All right, C-Block. So here's your first screencast from Chang. And what I need you to do is to go into your Dropbox and open up in Dropbox the file called, I think it's called L-Equation Writing and Predicting Products. And I need you to open that up inside of Notability. Now, if you're Hadley and you don't want to write this out in Notability, then, and I actually think it was there were a couple of you guys who didn't want to write things on your in Notability. But if that's the case, you're going to have to print out a hard copy of that document, which is kind of a pain. In fact, I would say you should try to use Notability and make it a little bit easier on yourself. So anyway, you're going to open it up in Notability. And then I want you to go to, I think it must be the fourth page where you're going to see the table that looks exactly like what you see right now in front of you. Because then you're going to start writing things into these boxes. And I'm going to explain them to you rather than just giving them to you. Okay? So go ahead and pause it for a moment, and then unpause it, and you'll hear me start to explain this, what's going on here. Okay. So we're all set and ready to go. Let's talk about the first reaction where we were burning magnesium. Now, if you remember in lab, when we were burning in magnesium, this is the one that it actually looked something like this. Okay, it looks something like this, if you can recall. Incredibly intense, bright light that you weren't allowed to look at straight on when you put the ribbon of magnesium into the flame. Okay, so let's move backwards to here. When you're burning something, whenever you see the term burning, and I'm sure that Oxborough went over this with you guys too, but when you see that term burning, it, oh, hold on, let me lock this out. Oh, I didn't mean that. Unlock it, shrink it back down. It immediately should trigger in your brain that this is a combustion reaction. Okay, so if we have a combustion reaction, that means it's combining with oxygen. Okay, now I'm going to lock it. Okay, so we have, let me erase this point here. We start off with magnesium, and in terms of state of matter, you know through your observations that the magnesium ribbon was a solid, so we put a subscript solid there. And then we need to add the oxygen to this process because it's a combustion reaction. And then we were left with a white powder, and that was magnesium oxide. Now, it's important that you understand how to do this, right? If you only have Mg and O in this process, then that means that when you combine the two to make the product, it's got to be a combination of Mg and O as well. But you can't just necessarily leave it like that. There might be subscripts that you need to put into place here. And the only way you can know that for sure is to go back and look at your periodic table and see that magnesium is one of those alkaline earth metals, right? And as a result of being an alkaline earth metal, we know that it has a +2 charge, and oxygen has a 2- charge. So when these things come together, they actually come together in a perfect 1-to-1 ratio. So I'm going to go ahead and delete this because you don't need to have this in your notes. But what that means is the MgO stays as it is, as you see it right there, MgO. Now, let's take a look here at some more states of matter. The oxygen is a gas. We know it comes out of the air. And as I said to you before, the MgO itself, magnesium oxide, is the white solid that forms after this reaction takes place. All right, so there you have it. Now, obviously, these are not balanced equations, but right now I'm not going to work on balancing them because I would like for you guys to do some practice and do that yourselves. But there you have it in terms of just predicting the products. So let's take a look at the next one. I'm only going to do a couple of these guys actually because you know they're only it's a fairly instructive process, but it gets a little crazy after a while, just too much. So we're going to do a combination of magnesium and hydrochloric acid for this next one. And obviously we're going to start off with the same magnesium, and we're going to combine it with our HCl. And our HCl, if you recall, was a solution. And if it's a solution where water is the major solvent, then we know that must be an aqueous solution. That's an AQ that I've got there. And then, very importantly, when this reaction took place, if you recall, this is the one where you did the pop test, where you collected a gas that was evolving from the reaction in a small test tube that was inverted over the top of the larger test tube, or maybe the other way around, I can't remember. So you collected the gas in this test tube, and then you lit a splint on fire and put it under the mouth of the inverted test tube, and it made a sort of high-pitched pop sound. And that is always an indicator, that high-pitched pop sound is always an indicator that hydrogen gas has been produced, because hydrogen gas is something that's flammable, fairly explosive in fact. So I can go ahead and put in my hydrogen gas. And then you look and see that there are some other things here. We have magnesium and we have the chlorine that needs to be involved in this. And in fact, what's created at the end is, if you remember, you had to actually look carefully at the observations of what was going on here. Nothing was produced, though it looked like when you put the magnesium into the hydrochloric acid after the hydrogen gas evolved, and you looked through again carefully at what was left over, it was a colorless and clear solution. And in fact, it was a colorless and clear solution, but that doesn't necessarily mean there was nothing in it. What was actually in it were dissolved magnesium and chloride ions. And the way we show that, and again, you can't know this, so this is one of those things you just have to learn through practice. You know there's Mg, and there's also chloride ions, okay, Cl. But just like I had to be careful about how to combine the MgO in the equation above, I also have to be careful about combining the MgCl in this equation, because in this case, Mg is still 2+, but the chloride ion is what? It's a halide, so that means it is a -1. So that means you need to have 2 chloride ions for every 1 magnesium to make it a neutral compound. So I'm going to go ahead and put a 2 for my MgCl2 there. Okay. Now, like I said, this MgCl2 was something that you couldn't see. Somebody's calling me. Hold on, just. Okay, that was pretty funny. Mr. Small had left his snake out of his cage and it was cruising around on the countertop, and he needed me to move him back into his cage. Okay. I don't exactly remember. Oh, yeah, MgCl2. So if you recall what I just said moments ago, the Mg and Cl2 are ions that have been dissolved in the water, and so if we have something that's dissolved in water, it's aqueous. Okay. All right. So, and in fact, that actually brings up another point, which is something I think you guys have talked about. Let me just scooch over to here an empty page, actually another empty page here. The MgCl2 undergoes a dissociation reaction, right? Not reaction so much, it's just a plain old dissociation. And when it breaks up, it turns into Mg ions hanging out in solution, plus the chloride ions hanging out in solution there. And now, another very important thing here is to not forget that this isn't a balanced situation yet, because I need to have 2 of the Cl's for every 1 of the Mg. All right, so that's a dissociation equation. I'm almost certain that you guys have done those things, so I'm not going to worry too much about that. But this is what's hanging out inside of the test tube, right? I've made a big, fat, shallow test tube there, but this is what's happening inside the test tube after you've combined the solid magnesium ribbon with the hydrochloric acid. Okay, so let's zip back to there. That's what I've implied there with my MgCl2. All right, so let me lock this back out so I can write properly in it. There we go, locking it. Okay, let's take a look at one last one here, because frankly the group here that I'm circling in pink, these are all pretty straightforward. They're all double replacement reactions where you just do the partner swapping thing. And so I'm not gonna bother talking about those ones for right now. All right, let's take a look at what happens when you heat the ammonium carbonate. All right, so we have the ammonium carbonate, two polyatomic ions. All right, so this is a compound that consists of two polyatomic ions. Whenever you see heating, that's another sort of word that immediately should make you sit up and pay attention, because heating is not the same as burning. Burning always implies that you're combining it with oxygen, whereas heating always implies that it's a decomposition reaction. Remember that one? It's AB leads to the break into A plus B. All right, so in this case, we're going to start off with our ammonium carbonate. So I'm just going to write out ammonium carbonate, the chemical formula for ammonium carbonate. Don't forget those parentheses. And I have to have two ammonium carbonate polyatomic ions because they are a +1 charge to go with my one carbonate ion, which is a -2 charge. So in order to have a neutral balanced compound, I always have to have two of those +1s to go with my one -2 ion. And this was a solid. Again, the only reason I'd expect you to know that is that you paid attention in lab and you were writing down notes about what it is that you were working on. And we started off with a solid, so obviously it must be a solid. But this is where it gets a little trickier, because there is a lot of stuff going on here. You may or may not have written down these observations, but had you been very careful about doing so, you would have noticed three very important things that we had you focus in on. Number one was that there was an odor that was emanating from this reaction, and the odor was the smell of ammonia. I'm sure many of you have smelled ammonia in a cleaning solution, so it's a fairly familiar household smell. But if ammonia was one of the things that you smelled, then clearly ammonia was one of the products. And ammonia is NH3, and since you could smell it, it was in the form of a gas. So NH3 gas. But then we also had you do a couple more things, if you recall. We had you take some what's called cobalt blue paper and put it over the mouth of the test tube as the reaction was happening. And that cobalt blue paper turned from blue to pink. And that's an indicator, you may or may not know this, but that's an indicator that water actually has evolved out of this reaction. So cobalt blue paper is an indicator of water coming out of a reaction, or water being a product. So we have H2O, and that too was in the form of a gas. And then lastly, we had you take a burning splint. So this time there was a flame coming off the tip of the splint, and we had you put it right over the mouth of the test tube as the reaction was occurring. And in that case, the flame went out. And that always is an indicator that CO2 is a product of your reaction. So through those three tests, using the nose test to smell the ammonia, using cobalt blue paper to indicate that water has evolved, and using the burning splint being snuffed out as the indicator that CO2 has been produced, then you can get your three things that you know came out of this reaction. And in fact, if you take a look at the reactants involved, you can see that all the different atoms have been conserved in this process. You see the N, the H, the C, and the O all come out. Have they combined into different things? Absolutely. And that's a pretty complex thing to be able to figure out how to do, right? To figure out how to determine what actually has been produced. You only get it with a lot of practice. That's the bottom line. Okay, so I'm going to stop here. And like I said, at some point we're going to look at these guys together as a group. And we're going to look at this as well. And so this is what I'd like for you guys to be thinking about. I am sure that you took notes on this. If you didn't, then you're in trouble. You should have taken notes. And what I'd like for you to do is to simply go back through these three reactions that you have written down on your piece of paper in Notability, and I want you to balance those equations. And then tomorrow, or on Thursday, I'll just come around and check to see that you actually have done that. Okay, crew, I'll see you all on Thursday.